Okay, yeah, here we are. So first, I would like to appreciate my co-authors, Jing Chen from Beijing, who spoke yesterday, and Dejan Milosevic from Sarajevo. And of course, I would like to thank Carla for the invitation, and Andrew Maxwell and Andrew Brown for the perfect organization. Everything that does not go well, like I had problems right now, is not their fault. When I received the invitation from Carla, I pondered a while what I should make of this babble. And so I consulted my favorite philosopher, Heraclitus of Ephesus, and the statements of his that have been preserved are few and are opaque. And one of his most best known statements is that a babble is the father of everything. I always had misgivings about this. I mean, this statement has been used and abused by the military for millennia, but now I know what he meant to say. It's exactly what we are experiencing here. Okay, this is what I want to do. And when I say SFA, I mean it in the very traditional sense, namely the Born series in the electron-ion interaction. No improvements, nothing else, just the Born series. And okay, here we go. It's very quickly derived. You start from the ionization amplitude, which incorporates the electron time evolution operator in the presence of both the binding potential and the external laser field. Now, of course, we don't know that. So in order to get a series, we just use the Dyson equation here and iterate it. And that yields the strong field approximation. And normally, one only considers the first two terms. The zeroth order term here is what's often called the direct term, or it describes the direct electrons, which means that the electron, after it has been liberated, doesn't see the binding potential anymore. There is a certain conflict here on the use of this word direct, and I'll come to that later. The next order term describes the once rescattered electrons. Here's a binding potential, and so this allows for one and only one interaction of the liberated electron with the core. And then you can keep going. So here would be the second order term, two interactions, etc. This actually was written down for the first time by Howard Rees in his seminal ADI paper of 1980. There are limitations of the SFA. Actually, there are very few in principle, because the series I wrote down is exact. So if you can sum it, you have an exact solution of the problem. One limitation is that we approximate the final state, which should be a continuum state with a binding potential, by a plane wave, the Volkov wave. Now, if you were able to sum the series, then the initial bound state would get dressed, and also excited bound states would appear in the picture. But we don't do that, we cannot do it, so these are limitations. The possible improvement is the low frequency approximation, which essentially replaces in the matrix element the potential by the corresponding complete T matrix, but without the field. So it's still an approximation. It's a series, so there is a problem of convergence, and I'll come to that later. Now, obviously, the SFA is better, the lesser the role of the potential is. So it's ideal for a negative ion, and actually it was conceived originally for a negative ion, weakly bound electron. And I show you a comparison here of, this is ionization of fluorine, the negative ion. And here's an SFA calculation, only the direct term. And here's an exact solution of the time-dependent Schrödinger equation. And you have to look pretty hard to notice any differences here. This is even though the TDSE includes rescattering here, but it doesn't play much of a role. Now, for a negative ion, the SFA is also good if rescattering is included. This here is an experiment by Igor Kiyan 10 years ago. And the upper part is the experiment. You see the rescattering plateau here. and the lower part is the theory, now including the first term. And again, on this scale, the agreement doesn't leave anything to be desired. Now, this is negative ions, but of course, we are interested in atoms. Now, even for an atom, the direct SFA is not hopeless. If you focus on the region here transverse to the propagation direction of the field, then you see here this pattern, which at the time we called the carpet. And the carpet again is very well described by the SFA. Here's the experiment again. Here's the TDE simulation. And here's the SFA. And only including the direct electrons, no Coulomb field after the electron got out. How come? That the situation is this, that at right angle to the field, if you were to Coulomb correct the electron states, then both direct orbits would be affected equally. So if you calculate the phase difference for interference, the Coulomb field would actually drop out in that case. Now in the field direction, it's a totally different story, because now the two orbits, the two direct orbits, are affected very differently by the Coulomb field. The short orbit is not at all, and the long orbit very significantly. I'll come to that later. Okay, the SFA, as I showed it, is already perfect. I mean, you have compact expressions, only integrals that you have to evaluate. But the integrals are strongly oscillating, and it simplifies the problem enormously, and also gives you a lot of physical insight if you evaluate the integral by saddle point evaluation. And in order to do that, you look at the oscillatory parts, the phase here that oscillates, the action actually, and you look for those values of the integration variable, which is the time of liberation, the ionization time, and the rescattering time, and also possibly the momentum in between. So you look for those values that render the action stationary. So that gives a couple of equations, and here it is again. So the first one describes energy conservation at the time of ionization. The negative sign here indicates that you are not going to get real solutions for these times. The second equation here describes the condition that the electron return to the ion at the time t, and this one here accomplishes elastic scattering at the time of return. So the solution of these equations, here they are in pictures again, the solutions of these equations define quantum orbits. Each solution then has to be inserted here into this phase. There's a prefactor which doesn't matter very much, and then you have to carry out the sum. The sum extends over all quantum orbits, and there's quite a number of them, infinitely many, depending on the situation. All of these have to be summed up. And each solution defines a quantum orbit, which just gives you the trajectory of the liberated electron in space and time, before and after rescattering. So that's a picture. Okay, these are complex still, but the real parts can be drawn. And that gives you a picture of what happens when you consider ionization into a state with final momentum p. So a summary is that it's an enormous simplification of the original problem. You only have to find the solutions of the saddle point equations. So rather than having to use the integrals, you just have to solve the system of two algebraic equations. And this works for any number of dimensions, any external field, any polarization, etc. And you get for free a very appealing, intuitive picture of the underlying dynamics. Now, of course, there is a word of caution. It's fairly easy to solve the saddle point equations for linear polarization. But in other cases, it can be very cumbersome, and it's easy to overlook some, etc. Okay. So for linear polarization, the simple man model gives you a very easy overview. And normally this picture is shown in this context here, where you have here the start times, and then you have the various electron trajectories departing off the ion, returning, never returning, etc. But I prefer this picture here, which has a lot more information in it and is much simpler. What's plotted here, the curve, is the integral of the vector potential. If you have a monochromatic long pulse, then this is proportional to the electric field. You specify the start time here, right here, and then you put the tangent to this curve at the position of the ionization time, and you look for the intersections of this straight line with the curve, and that gives you the recollision times. So in this case, there are 3 solutions, and now here comes a very important point. I showed you that the first order rescattering term only accounts for electron-ion interaction once. So this here actually corresponds to 3 terms in to the ionization amplitude corresponding to this, or this return time. And if you would like to have the term that accounts for the fact that, for example, an electron that returns here has already seen the ion twice before, then you would have to go to the 3rd order term in the expansion, which nobody has ever done. So that's a limitation which is often overlooked. One has to discriminate between rescattering and revisiting. An example of the fact that you need to consider sometimes very many solutions is very old here. Data are from the last millennium. What's plotted here is a part of the ATI spectrum for different intensities. Intensity goes up here from the lowest to the highest trace by only 5%, and you see that this group of peaks here rears up by almost an order of magnitude. And here's an SFA description, which works pretty well, I think. And also, you can now make a statement about the underlying physical reason. You get this picture here by summing over a large number of these longer orbits. And the enhancements, the parameters have to be such that you are at a channel closing, and then and only then you get a constructive interference of all these higher order contributions. This is for linear polarization. Here's a corresponding picture for a bicircular laser field. Again, if you consider constant electron energy, for example, then you see here these enhancements coming up at intensity differences that correspond to channel closings. Another example of what the SFA can do is the low energy structures. We look again at this picture here, and okay, you start here at the ionization time with a tangent. This corresponds to the fact that the electron starts with zero velocity. Now it's possible, like in this case, that the electron also returns with zero velocity. So that would be a soft recollision. And now if you modify the start time only very slightly, then the picture is this. So the soft recollision has dropped out of the picture. So this situation here corresponds to a cutoff of the spectrum. You have a solution contributing up to some point, and then it drops out. So in classically, this is sharp. Quantum mechanically, it's smoothed out a bit. And these cutoffs are visible in the spectrum and define the low energy structure. You also see here that such a soft recollision is invariably preceded by a hard recollision, which, however, is not part of the picture once if you are restricted to the first order term. Okay, you can keep going here to the, here this again would be another soft recollision about one period after the first, and that way you get a whole series of LES, which corresponds to the case that has been seen in experiments and also been obtained by other approaches. Let me return for just a minute to the direct orbits. So these are the orbits here that correspond to direct ionization. It's 2 per cycle, and they lead into the same final momentum state because the final momentum is given here by the slope of these straight lines. And now here you see the short orbit and the long orbit. The long orbit revisits the ion, but this is not part of the description by the 0th order term. And if you want this to be part of your description, you have to move to the first order term. Now in the first order SFA, the same orbit also contributes here to rescattering. This can be forward rescattering, and then a superposition of the direct orbits from the 0th order term, and this here from the first order term will generate the famous holographic structures. So I would like to emphasize that different people understand different things by the direct orbits. For SFA people, these are the two orbits that contribute to the 0th order term. If you are a trajectory guy, I mean a CTMC person, then this orbit here would interact with the potential all the time. So depending on the situation once, or if it goes this way several times, and all would be the same time, and people call this the direct orbit. So one needs to be aware of this difference in language. Okay, back to the cutoffs. Now here's a pretty complicated picture, but it's still the simple man picture. And now here the lines denote all the cutoffs, so that solves the saddle point equations, also as a function of angle. So let's return to the, I have some notation here for these orbits, which however I don't have the time to explain, never mind. Let's look at the simplest situation here, that's up here. So here are the high energy cutoffs of the plateau. You see here the light blue line is a 10 UP cutoff, and then you have a series of other cutoffs at lower energies that correspond to longer and longer orbits. They converge ultimately to a limit here of 8 UP, which is a dashed line. Then here, if you change the angle, you see what happens to these cutoffs. And the situation here near the origin is especially rich and colorful and interesting. And let me show you a blow up of this, which is right here. And now here you see a lot of first, I mean, you recognize the LES series. In the field direction, it's here. And if you move off axis, then these energies move. So then here, there's a lot going on. We call this the fork at the time, because here is sort of one bunch of cutoffs here and another one here. And in the middle, this forms the middle prong of the fork, and it splits up again. And all of this is due to longer orbits. And then you have one by here, you have a V structure that I'm going to show you, etc. So all of this is a simple man model. Here, for example, is an SFA calculation of this V structure, which you can nicely compare with the data in this paper by Volta et al. And here's a fork. You see it here. And in this picture here, we have tampered with the color coding a bit. So now here it jumps out more clearly. You also see here the spider. And here you were to see the LES if the solution were better. Now, this here is for a fairly long pulse. It's interesting what happens if you shorten the pulse. Here it's down to 2 cycles, and you see the fork is gone. And the reason is, again, becomes very clear in terms of quantum orbits. The fork is generated by longer orbits. And for a short pulse, the longer orbits just do not have time to unfold. The spider, on the other hand, survives. So that's generated by short orbits. Here's the famous holographic structure paper, and actually it also shows all these features here. Even I think they were not addressed in that paper. Here is the SFA calculation, including the zeros and the first order term of the Born series for a long pulse and for a short pulse, and you see all these structures here that I was just pointing out. Now, you may have noticed that I did not mention the potential with just one word, even though many people will tell you that the low energy structures are due to the Coulomb field. Now, this is partly wrong, in my opinion, and partly not. And the reason is this here. Normally, of course, the rescattering term is completely dwarfed by the first or by the 0th order term in regions where both contribute. And but this is not necessarily so if you have a Coulomb potential, because the first order term incorporates the scattering amplitude, and that goes like 1 over the momentum change squared. and it's actually divergent for forward scattering. So this acts here like an amplifier of the rescattering term and has a consequence that these low energy structures are indeed visible on top of the direct electrons described by the first term. Okay, another example, let me consider ATI in a bicircular field. Here finding the solutions is much more complicated. Okay, here is the electric field, the black line. We consider equal intensities here, and the vector potential. And the zeroth order term, which the spectrum of which is given here, you expect the spectrum to be opposite to the vector potential. So the electron comes out preferentially exactly at right angle to the maxima of the field, as you expect. Now, this is a first order term, is a zeroth order term. And you also see it has two kinds of symmetries, rotational symmetry by 120 degrees and reflection symmetries about 3 different axes. Now I turn on the interaction term, looks like this, and you see immediately that the reflection symmetry is gone. And you also see here that the electron, if you superpose the two terms, the electron would no longer come out in the direction of the vector potential, but there would be some offset angle here, which depends a lot on energy. Okay, another feature here are quantum orbits that are contributing to ATI in a bicircular field. And okay, let's see what these orbits do. This here is the result of zeroth order plus first order calculation. Ideally, this would correspond to an experiment. So let's assume that an experiment would also look like this. And now you want to know what is the origin of certain electrons here in this velocity map? How do they get out? What do they do once they are in the continuum? So in order to answer that question, you can separately plot the contributions of individual quantum orbits. So here are 3 examples. 2, this is forward scattering. This is forward scattering at comparatively low energy. And this here is a backscattering orbit. Now you can superpose these, so that gives a picture like this. And now you can indeed draw the conclusion that this feature here in the measured, ideally, spectrum is actually generated by these quantum orbits. And these quantum orbits here look like this. This here is this picture. All the orbits are drawn for an ultimate angle of 50 degrees outside the field for the electron to make with the polarization axis. So you can actually, for any part of this velocity map here, you can identify the corresponding dynamics of the electron in the continuum. Okay, change of gears in my last minutes. Let's just consider pure Coulomb scattering, no external field. So if you want to calculate the cross-section, then you have to sum these Feynman diagrams here. The first one is quickly calculated and gives a standard result, the Rutherford cross-section. But now you want to do a better job and also include some of the subsequent diagrams. And then you will notice that these contributions here actually diverge term by term. And if you somehow tamper with this divergence, then you will get a result that is wrong. It differs from the Rutherford cross-section. So the upshot is that in this case, this holds for a Coulomb potential and only for a Coulomb potential. The first order already gives you the exact cross-section. And turns out that if you want to do it, you can actually, with some screening or something, to handle the divergence, you can calculate all the higher order terms, sum them, and then you will notice that the sum, all the divergences are absorbed into a divergent phase, and the prefactor of the phase just corresponds to the Rutherford cross-section. So this is a unique situation for a pure Coulomb potential, related obviously to the fact that the Coulomb potential has no parameter in it. no parameter of a length or anything. Okay, now if, of course, we want to do this on the background of a laser field. Doing this is very easy. You just have to replace a straight line by a double line, which indicates the Volkoff propagator. And then you have to try to do the same thing with the Volkoff propagators, and that's of course no longer easy. And okay, the hope or the question is, would the same mechanism still apply? And the answer is, of course, no, it won't. But on the other hand, I believe that this Coulomb mechanism is still lurking somewhere just below the surface. And it should make itself somehow noticeable when you do all these higher order calculations. Here is a recent calculation by Jing Chen and collaborators, and he actually managed to calculate the first 5 terms of the Born series corresponding to 0, 1, 2, 3, 4 real rescattering events, not just revisits, rescattering events. And here you see the results. This here would be the direct electrons, and then as of one interaction, you have the plateau. But now, if you include more and more terms, it grows. And this, of course, the suspicion is near at hand that if you keep going, the series will diverge. I mean, in order to avoid it here, he screened the Coulomb potential a little bit. Okay, so the suspicion is that for a Coulomb potential, actually the Born series will diverge. So what should be done about it? Well, we don't really know. The idea would be ideally to manage to sum all the forward scatterings of the electrons in order to get something like a renormalized electron propagator. And so then forward scattering would be removed from the interaction, and then hopefully the Born series would quickly converge in terms of this renormalized interaction. But well, this is science fiction, and we have not been able to do this. Okay, so I promised kind of a list of what effects are covered by the Born series and what are not. And here's a list for effects that are incorporated, that can be handled with the Born series is quite long. And the opposite list is much shorter. It definitely, I think, includes this 1 to 2 UP plateau, which was recently discovered by the chairman and by Sergei Potrushenko and Thomas Keil. And I think also the very low energy structure should be on this list, but I'm not quite sure about it. And also the zero energy structure. Okay, let me just finish by showing a list of references. Here, of course, top of the list is this beautiful review by Carla and Andrew Maxwell. And that has everything in it that they tried and other people have tried to improve on what I was talking about. And there are other review papers here, and there are other papers that I consider important. And so thank you for your attention wherever that might have taken place in space.
Thanks very much, Wilhelm, for this nice overview. So we have time for a few questions. I see one question by an anonymous attendee. It's difficult to unmute an anonymous attendee, so I just read it. Could you please comment how comes that the 2-cycle pulse photoelectron distribution is so symmetric? Is this just 2 cycles out of infinitely long constant envelope taken into account?
The reason in that case was that they averaged over the carrier envelope phase. So that otherwise, I mean, if they had had a specified CEP phase, then depending on the value of that phase, they would have observed forward-backward asymmetry. But I think in the data it was averaged.
Okay, the next question is by W. Kwan, so probably we can unmute you so you can ask yourself. Please speak. Okay, then I just read it. Would you mind discussing more on the uniform approximation? What kind of problem can be solved by it?
Okay, hey, hi, Wei, that's what you are, right? Anyway, so the uniform approximation, I didn't have time to explain it. I cited a reference. The uniform approximation is important when two saddle points approach one another very closely. This is always the case near a cutoff. Okay, and then the standard saddle point approximation doesn't work anymore. Actually, what you have to do is at some point, which you have to pick deliberately, drop one of the saddle point solutions. Otherwise it blows up. And if you use a uniform approximation, then this does a job for you. And it treats the two saddle points as one unit and automatically disposes of one after the cutoff. Carla, by the way, is the expert on this. She has used it in very many papers, and it works beautifully.
Okay, the next question is by Jens Biegert. Jens, please.
Good morning, everybody. Very nice talk, Wilhelm. I was just wondering, the bicircular field that you showed and this angular offset of basically the emerging electron wave packet, how it goes out. Do you think this could be a useful probe of more of the structure of a Coulomb field, for example, of a molecule, even if volume averaging would come into place?
Well, volume, excuse me, volume averaging, of course, is a problem. I mean, I think actually, but I don't know, because we hadn't really made this connection until quite recently. I think that if you use the Coulomb potential for this calculation, then it would give you the right offset. I mean, the one that you also receive by solving the TDSE or so, I mean, to the extent that the SFA is applicable. But we haven't done this, and okay, for a molecule, the SFA can be done, has been done in many papers, but it's a bit problematic because for a molecule, the inherent gauge dependence of the SFA makes itself visible in some obnoxious way. But actually, you remind me of a point, I mean, which I forgot to mention, that in my opinion now, the treating the Coulomb potential just to first order in the first order rescattering term is much better than people, including myself, used to assume until recently. And the possible origin is what I was talking about in the end.